Hello dear students, I welcome all of you to this second video on multistage graph. In the last video, we saw definition of multistage graph and the properties of multistage graph. Here we are. This was an example and few definitions I gave in the earlier video. Now we left that video with a question that what is the shortest distance from source vertex? Here we go, source vertex to the destination vertex. And we want to find out the answer. And we are going to use the algorithm called forward algorithm for doing that. The forward algorithm is going to use two arrays, D and P arrays. Now D stands for distance and P stands for path, but I have labeled it in short. D is the array of 7 vertices as there are 7 elements. I'm sorry. D is an array of 7 elements as there are 7 vertices. So we say V is 7 here. Number of vertices is V and V is 7 in this example. And P is a path array which also has 7 elements as there are 7 vertices. Actually, the meaning of this D array is important to be known. What is D array going to store? Now listen, this D array is going to store distance of any vertex, but that should be shortest distance of any vertex to destination vertex, that is seventh vertex. For instance, let me explain. For example, what is D4 going to store? Let's say. By the way, before that, you can see that the names of the vertices in this example are S, A, B, C, D, E, F or ET. But I have renamed these vertices as 1, 2, 3, 4, 5, 6, 7, as you can see written in red in the diagram, so that we can actually index the array properly. Coming back to our discussion, what is D4 going to store? D4. Just check the fourth element of D. Now the fourth element of D is going to store shortest distance from fourth vertex. Here I am encircling that fourth vertex in our example here. C is that fourth vertex. What is the shortest distance from this fourth vertex to the destination vertex? The destination vertex is vertex T. And you can see that there are two ways in which you can go from fourth vertex to the destination vertex. One method is you can go directly, yes, with a distance of 10. Distance is 10 here. And the other way is that you can go via vertex E. You can first go from 4 to 6 and then 6 to 7, isn't it? So what will be the shortest distance over here? Now notice that the distance between 4 to 6 is 3, and distance between 6 to 7 is 2. So the total distance is going to be 5. So actually if you go from 4 to 7 in our example, if you take the if you take the direct path over here, you are going to take a distance of 10, isn't it? But if you go via sixth vertex to T, then you are going to take distance of 3 plus 2, that's 5. So actually D4 is going to store value 5. What does that mean? Is if you want to go from fourth vertex to the destination vertex, that is vertex 7, then you can go from 4 to 7 using minimum distance 5. 5 is the minimum distance from vertex number 4 to vertex number 7. That's the meaning of D array. But then P4, observe the other array P4, this element P4 is going to store 6. Now why exactly? Is because you know that from shortest distance from 4 to 7 you know is 5, isn't it? How did you get that? Shortest distance from vertex 4 to vertex 7 is just 5, 3 plus 2. But how did you get that? You got that by using vertex number 6 as the intermediate vertex, isn't it? So hence, if you want that minimum distance of 5 from 4 to 7, you will have to take the help of vertex number 6. That's why P4 has been initialized as 6 here. I hope you understood. Let's take one more example. What does this indicate? What is the meaning of D array and P array? Let's try to understand that. Okay. Let's see what is D3 going to store. Well, D3 will store shortest distance from 3 to 7. Now have a look at this. We have vertex number 3 here. I will rewrite it. Vertex number 3. That's vertex B in our graph. Now your aim is you want to go from B to the destination T using least distance, isn't it? Now there are these many ways. You can go from 3 to 5 and then 5 to 7. So what will be the distance? It will be 4 plus, it will be 4 plus 8, that is 12, isn't it? 4 plus 8, which is 12. I'll just increase the font if in case this is not visible. Oh, I hope it is visible now. So what exactly are we doing when we are finding the best distance of D3 here? The best distance of D3 has to be found out, isn't it? Now, if you want to find out D3, then the first way of doing this is you can go from 3 to 5, yes, 3 to 5, and then 5 to 7. So total distance of 12. This is via fifth vertex. This is 3 to 7 via 5. What is the other way? You can go from 3 to 6. This vertex is 6, and 6 to 7. What is the total distance? Again 12, isn't it? 12. That's going to be via 6. I hope you're understanding. And there are no other ways by which you can go to vertex number 7. You can either go to D or you can go to E, that is either go to 5 or go to 6. So anyway, you are going to get minimum of 12. So hence, this D3 is going to be 12. D3 will be 12. But what should be P3? Now P3 can be either 5 or 6. It doesn't make any difference because this 12 or this 12, the minimum you got by the use of fifth or sixth vertex. That's what is the meaning of D. So in general, what does DI indicate? DI means shortest distance from I to destination. That's the meaning. And DI here will be obviously assisted by PI. PI will give you the intermediate vertex that helped you to find out that shortest distance. Isn't it so? So coming to a very, very important question, what is going to be D7 here? Think about it. What is D7? Now tell me, isn't D7 meaning shortest distance from 7 to 7? Because D4 means shortest distance from 4 to 7. D3 means shortest distance from 3 to 7. Isn't it? DI means shortest distance from I to 7 because 7 is our destination. So basically D7 is going to be shortest distance from 7 to 7 and that has to be 0. So the algorithm will begin by initializing D7 as 0. D of destination should be 0, indicating that the distance from destination to destination is 0. And then our algorithm will keep finding the values backwards. It will first find D6, then find D5, then find D4, and finally find D1. Now, once D1 has been found, when D1 will be found, we know that we have found shortest distance from 1 to 7. Come on, what is the value? What is the meaning of D1? D1 means shortest distance from 1 to 7, and that's what we wanted to find out. But this will be found only after finding all the values in reverse like this. From sixth vertex, we will come backwards up to first vertex, and then we will get the answer. So surprised actually, I was surprised when I saw the word forward here. I told you that this algorithm is called as forward algorithm. But actually, in our processing, we are coming backwards here in our array. We will start from sixth vertex, find out the value of this element, then come back, find out value of fifth vertex, and so on, and reach first vertex. Then how is it known as forward algorithm? It should be known as backward algorithm, isn't it? But actually, the reason behind calling it as forward algorithm, because it will finally give us the path from source to destination in forward direction. Oh, yeah, you will understand what I'm talking about. Okay, but keep this in your mind. Why is it known as forward algorithm? I'll tell you, trust me. All right. So now let's find out the processing of this and how is this algorithm written. Keep an eye on the algorithm now. Now the algorithm over here, is actually saying that let's imagine that we are having v vertices. V vertices are there, and let D and P be the arrays having V elements each. So in this example, D array, I will redraw it, will have 7 elements. There are 7 elements in D array, and there are 7 elements in P array. And the next statement written in the algorithm must be known by you already now. What is written in the algorithm here is that let dv be equal to 0. dv means d7, isn't it? Number of vertices. So d7 is initialized to 0. What that means is distance of 7th vertex to 7th vertex is 0. And now starts the interesting part. Just check what we are saying here. We will write a for loop. We are having a for loop here where a counter x simply goes from v minus 1 back to 1. So in our exercise, x is going to go from 6 back to 1. X is going to go from 6, v minus 1, isn't it? Down to 1. So we are going to make x as 6, then x is 5, then x is 4, finally 1. And each time x is at some element of the array, we are going to find out that element. So when x is 6, we will be finding out d6. When x is 5, we will be finding out d5. Now let's see as an example, how do you find d6? That is when x is 6. Let's start this loop. X is 6. And I think the sixth vertex, if I am not wrong, is this one. Let me label these vertices. 1, 3, 4, 5. Okay, let's label this as sixth vertex and destination is 7. We want to find out d6. What does that mean? We want to find out best distance from 6 to 7. Come on, the best distance is the only distance that we are having, because there is only one way of going from 6 to 7 and the shortest distance is 2. Correct or not? So there is absolutely no difficulty in seeing that the shortest distance from 6 to 7, that is d6, has to be 2. But how does the algorithm say about that? You can see that what we do is we take every edge of the form x comma y. Read out this sentence. When x is 6, observe now x is 6, we take all the edges of the form 6 to y. So the edges which start from 6th vertex and end somewhere, isn't it? For every edge, we will check what is the weight of that edge up to its neighbor, and we will add up the distance of that neighbor which has been already found in the previous pass and compare it with a very large value min. So I will just trace this for you. Right now x is 6, correct? We have started our for loop for x equal to 6 back to 1, down to 1. X is 6. Now let's take all the edges of the form 6 comma y, but there is only one edge, 6 comma 7. Observe, there is only one such edge in our graph which is of that form which begins with 6 and ends at y. Y here is 7, correct or not? In short, take all the outgoing edges from vertex number 6, and there is only one outgoing edges. Observe the graph from vertex number 6. And now what we do is we check the weight of x comma y. What is the weight of x comma y? 2, given in the graph. That is 6 to 7 is having a weight of 2 plus d of 7, because y is 7 in this example, and you know d of 7 is 0. So we are asking, is 2 plus 0 less than min? And min has been initialized to infinity, and this is obviously true. So what we are going to do is we are going to update the min. Min was initially infinity, and we are now going to update the min to that new distance, which is 2. We say that minimum has been updated to 2, and px, that is p6, observe this step, p6 is going to be 7 because this minimum we got for the 7th vertex. So the 6th element of P is 7. I hope you have understood. Now, the best way to understand the operations of this algorithm is not by seeing vertex number 6, which was having only one vertex. Let me erase a few things here. The best way to see how the algorithm works in detail is by seeing some example where there are lot of outgoing edges, isn't it? So for that matter, what we will do is we will imagine that we have found d6, d6 is 2. We have found d5 also. Now what should be the shortest distance from 5 to 7? Come on, there is only one edge, isn't it? And that is the best. So it's going to be 8, and p of 5 is also going to be 7 because there was only one option which was 5 to 7. Imagine fourth vertex. What should be d4? D4. I think we have found out this answer. The best distance of the fourth vertex to the seventh vertex is you go to 6 and then you go to seventh vertex. That is 3 plus 2. That's going to be 5, isn't it? 3 plus 2. So you can take this via vertex as 6. So fourth vertex is hardly 5 away from seventh vertex, but the via vertex you took for the fourth vertex was 6. Isn't it so? Okay, now let's see how this D3 is found by our algorithm. Patiently, you just see how this D3 would be found out. So if we are finding D3, surely in this for loop, x is 3, correct? The value of x is 3. And what is it saying? When x is 3, when x is 3, consider all the edges which begin with third vertex and end somewhere to y. So which are the edges? Which are the edges which begin with 3 and end somewhere? Let's go to our graph and see. We have an edge from 3 to 5. Observe this. 3 to 5. And we have an edge from 3 to 6. So there are two options. That means we are going to consider these two edges because it's written for every edge x comma y. So we have 3 to, I forgot, wait a minute, 3 to 5 and 3 to 6, isn't it? We have these two edges, 3 to 5 and 3 to 6. And for each of this combination, we find out what is the value of weight of x comma y plus dy. So what should be here? Weight of 3 comma y, isn't it? I'll write w3 comma y, weight of 3 comma y plus d phi because y is phi here. What is weight of 3 comma phi? Let's see. 3 comma phi is 4. And here comes the fun part. Weight of 3 comma phi is 4. And what is d phi? Now the fun part is 4 plus. Observe d phi need not be found because d phi was found in the earlier past. Check this, d phi is 8. We have already found. That's dynamic algorithm. 8, which is nothing but 12. And what about 3 to 6? Now 3 to 6, we are again going to consider this if condition is what is the weight of 3 to 6 plus d6, and check the example. The weight from 3 to 6 is 10, isn't it? 10. Now this 10 is added to d6, but we don't have to find out best value of d6 because d6 has been found in the earlier past. Remember, d6 has been found, which is 2 here. So this 10 is simply added to 2, and the best distance we get is 12, and we find minimum of these two options. That's what it is doing here. It is finding minimum of all the options that we can take if we are considering third vertex and we want to reach the seventh vertex. And anyway, minimum here is 12 comma 12, so minimum is 12. So d3 is going to become 12. I hope you have understood. D3 is going to become 12. But how did we get this distance? This distance was via phi or via 6. It doesn't make any difference, isn't it? So we will put phi here. 6 was also okay because both will give us the minimum distance. Once you have understood this processing, now the next step will be x will be 2 here, isn't it? let's do this exercise for x equal to 2 and x equal to 1, because x equal to 1 is going to give us the final result, isn't it? So let's make x as 1. When x is 1, sorry, x is 2, I'm so sorry, x is 2. Let's see where are the vertices of edges of the form 2 to something. In our graph, we are having vertex number 2 as vertex A, and we are having 2 to 2 to 5 and 2 to 6. Only two edges are there. So 2 to 5, as you see, is 3, and 2 to 6 is 6. So 3 and 6. So 2 to 5 and 2 to 6. Now the weight over here is 3. And what is d5? d5 we have already found in the earlier pass, and d5 is 8. This is going to be 3 plus 8, which is 11. And 2 to 6, the distance is 6 plus d6. And observe, d6 has been found in the earlier pass. d6 is 2. So this is going to be 6 plus 2, which is 8. And the minimum of these two is 8. And we got it via 6th vertex. So second vertex is going to be at distance of 8 via 6th vertex. Now finally, what is going to happen when x is going to become 1? When x is 1 in this for loop, when x is finally 1, we will see all the vertices of the form 1 to some vertex, isn't it? So which are the edges which are of this form 1 to something? You can see we have a edge from 1 to 2, correct? 1 to 2, 1 to 3, and 1 to 4. And the distances are 1 to 7. So we have 1 to 2, 2 to 3, and 3 to 4. Correct? And distances between, check it again, distances are 1, 2, and 7. So distance between 1 to 2 is 1 plus d2 we are going to check. This 1 to 3 is 2 plus d3 we are going to check. And 1 to 4 is 7 plus d4 we are going to check, isn't it? But d2 has been found in the earlier pass. d2 is 8. So this is going to be 1 plus 8, which is 9. And d3 has been found in the earlier pass. It is 12. So this is going to be 2 plus 12, which is 14. And finally, d4 also has been found out, which is 5. So this is going to be 7 plus 5, which is 12. The minimum is 9. Minimum of these three options is 9. And we got this 9 minimum distance for second vertex. That is, if you want to go from 1 to 7, listen, if you want to go from 1 to 7, you better go via second vertex. So we will get minimum distance here, d1 is 9, but that should be via second vertex. And 9 is our answer, isn't it? 9 is our answer. Interesting, isn't it? Now, finally, if you have found out the minimum distance from 1 to 7 is 9, what was the path? Now, path can be easily found out using the path array. Let's label these as 1 to 7. Path. Then, how do you find out the path that gave us this distance of 7? What you do is you start from P1. Check what is P1. P1 is 2. As P1 is 2, you find out what is P2. Now, P2 is 6. Observe. And what is P6? P6. P6 is 7, but 7 is your destination. That means you should go from 1 to 2, then 2 to 6, and 6 to 7 to reach your destination. And confirm it 1, 2, 6, 7 is the path which is going to give us the shortest distance, isn't it? I'll redraw this. It is definitely 1, 2, 1, 2. After that, it is going to be 6, 6, 7, which is 1 plus 6 plus 2, which is 9. How was the path really given? The path was given from source to destination in the forward direction. It was given in the forward direction, isn't it? Now, there is another algorithm which is known as backward algorithm. Now, backward algorithm also gives us the same answer, which is 9, shortest distance. But when you find out the path, it will give us the path from destination to source. Please try to understand. It will give us the path from destination to source. Same path it will give. Same path it will give, but it will give us the path in reverse direction. So that algorithm will be called as backward algorithm. Anyway, whether you use forward algorithm or backward algorithm, it makes no difference. After all, both are going to give us the same answer, which is 9, isn't it? Now, before we leave this discussion of the algorithm, what should be the time complexity of this algorithm? Now, the time complexity of the algorithm lies over here. Observe this. But I'll just erase the slate now. It's better. Okay. The time complexity of this algorithm lies in this for loop here. Because for any given vertex x, whenever we are finding dx, that is distance from x to destination, best distance from x to destination, we are considering the edges of the form x to y, correct or not? Now, basically what we are doing in this multi-stage graph algorithm is we are processing every edge. Listen very carefully. We are processing every edge exactly once. For example, if in this given graph, if we have already considered this edge in the earlier past, we are never going to consider this edge again. Any edge you observe is considered only once. So basically, if there are e edges, number of edges are e, this algorithm is doing nothing but it is processing e edges. So basically, the algorithm works in the order of e, big O of. That's good, isn't it? So if a graph has some, uh, say, seven vertices and it is having hardly 10 edges, then it will be processing only those 10 edges. The worst case of this particular algorithm will arise if the graph is really dense. Let me clear something, few things. That is, big O of E can happen to you in the best case. But what if the graph is really dense? The dense graph here means that there are, as an example, a dense multi-stage graph is this is source and this is the next stage. There are a lot of vertices in the next stage, and 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 the source vertex is having an edge to approximately every vertex in the next stage. And then again there are many vertices in the next stage, and each vertex is having the edge to all the vertices in the next stage. So the graph is really very dense. In that case, what you will see is that number of edges approximates to number of vertices. I hope you are understanding. Number of edges approximates to v into v minus 1 by 2 if it is a dense graph. So hence we have found out what is the algorithm called forward algorithm and what is its time complexity. Thank you very much.